basically, it's been very interesting finding out how similar, or how many things to do with cookery are scientific, to see what things that Paul does on a daily basis that basically amount to chemical reactions.
Yep.
Adding sodium citrate to things to reduce the amount of acidity, for instance, that's something we do in chemistry. We call that buffering a solution. So I've been looking a lot at the way food production relies on science and seeing how advanced the actual techniques that they use in food production are. More so than munitions, fuels, and lots of other, like the chemistry industry. So obviously it's driven by money. So inventions for sweets, driven by money, make far more money than possibly some pharmaceuticals, I don't know. I'm sure they have done over the decades. So we've been looking initially, I think our conversation started at this point,
yeah, it did, yeah.
About popping candy. How does popping candy work? And I thought, I don't know. How does popping candy work? I thought it was some chemical reaction that when it got in your mouth, it formed CO2, carbon dioxide, by reacting with some chemicals in here, like bicarbonate or something. But no, when I looked into it, I found what they did in these factories was put sugar candy under huge pressures. I mean, huge, very expensive, high pressure, like 600 psi, wasn't it, we were looking at?
Yeah, and if you imagine a car tyre is about 33 psi, so the pressure is immense.
And there were industrial processes that don't use, that are done under high pressure that don't use that much high pressure. So it puts it in context how advanced a lot of this sort of scientific thinking is, food science.
The other thing that I think we found along the journey was that you talk about the advances in molecular gastronomy, and people are talking about this in recent years as the revolution of this type of food preparation. But this is quite old, isn't it? A lot of these implements that we found, they've happened for years,
yeah.
And they were born out of scenarios which you just wouldn't expect. So we managed to build the panels on the basis of what is popping candy.
So basically, very high pressure, but it's quite obvious really how they make it. They get carbon dioxide, pump it through this sugar candy at very high pressure. Very expensive process. And then when it goes into, and then it sets very hard, and then when it goes into your mouth, it melts, and the carbon dioxide pops out.
Chloe?
So, I mean, I suppose it's a little bit like sort of frozen pop.
Yes.
In the sense that it's pumped through the carbon dioxide. Oh, can I have a bit?
Yeah, absolutely. And the other thing that we're...
Blast from the past.
If you'd like to intensify the reaction in your mouth, add a little bit more CO2 and take a little sip of the Sprite. Because then you'll see how the CO2 that's released from the high-pressured popping candy, plus you introduce a little bit of CO2 from the Sprite, what have you got? More. So you get more of a reaction. So have a little taste of the popping candy as it is, and then add a little bit of Sprite.
Has anybody ever heard of the reaction between Mentos and Coke? It's often a YouTube thing, isn't it? It's if you drop a Mento into a bottle of pop, it shoots out everywhere. And this is all down to the fact that a lot of people think it's got to be a chemical reaction, just like I thought with this pop. But actually what's happening, come in, but actually what's happening with the Mento is it's providing a surface for all the carbon dioxide to come out.
Put that in your mouth and have some Sprite.
So instead of the carbon dioxide leisurely sort of coming out of solution, you come around this way if you want. Oh. Instead of it coming out of solution nice and leisurely, when you drop a Mento in, there's this surface that it can suddenly come out of solution on. It's almost like crystals growing. They need a surface to grow on. And we call that catalysis, basically, a catalyst. That Mento is behaving like a catalyst. But I think what we're looking at today, we're looking at a little bit of history. You call them stabilizers.
We do.
I probably call them thickeners or something like that. But
they've got, I mean, in our industry, they've got many different names and E numbers as well.
Yeah.
So throughout the 80s and 90s, these chemicals were referred to by an E and then 3 numbers after it. So E110 would be sunshine orange, which is your food colouring. And then I think, is it E112 is the stabiliser for mayonnaise?
Is that xanthan? Xanthan gum.
Yeah.
Yeah.
So that's why you can open, I mean, as chefs, you know how long we have on a shelf life on mayonnaise. At the most is 3 days, yeah? Because you're using a product that's going to oxidize, it's going to start to deteriorate, and it's going to spoil, okay? So putting this xanthan gum into Hellmann's mayonnaise, you can open the jar, you can leave it in your fridge, and how many of you leave it for weeks and weeks and weeks?
Months. Come back
Yeah.
next year. Yeah.
And it's absolutely fine, yeah? So it's a stabilizer. But we'll talk a little bit about where these stabilizers come from,
Yeah.
what they're extracted from, and different uses for them.
And what effect they've had on cooking. Because to be honest, I mean, I'm only like a layman in this respect, but if you look at all the different styles of cookery that have happened over the decades, really they've revolved around the stabilizers that have been used.
Yeah.
And the stabilizers have often come from other areas like industry. Xanthan gum has always been, well, not, I don't know when it was first discovered, but it's been used big time in food production. And the things we're going to talk about today have come from various places like science,
Pharmaceuticals.
pharmaceuticals.
Yeah.
So, I mean, for me, when this started, what we're talking in terms of sort of science meets food, like World War II. Maybe
Yeah,
with,
definitely. I mean,
with the favourite. Yeah, the albumin, which, if you ask anybody over the age of, I don't know, 70 perhaps,
Yeah.
they will tell you that one of their favourite foods is dried egg. Because when they grew up in the war, they couldn't really get hold of egg. And if they could, they went to great lengths, didn't they? Varnishing eggs, anything to preserve an egg. But as a youngster growing up in the Second World War, you would be eating a lot of this dried egg, which, to be honest, I've had it, has a fantastic, intense, eggy flavour, And Paul will show you, you can use it in a more contemporary way to stabilise food better than egg would. Yeah, so you can make a meringue with dried egg, or at least part of a dried egg, which is the white of the egg, isn't it? The albumin. You can make a better meringue from using the albumin than you can from using the egg.
And the fact of the matter is, I mean, it's notorious within the industry that we follow trends. So something will come around, a new product, a new introduction that somebody's discovered to do something with. They put a label on it, and then all of a sudden, the price goes up. Okay? So this product here is sold at quite a high price as the perfect way to make perfect macaroons.
Why I use that then?
Working at Betty's, do you make your macaroons from
Fresh eggs?
fresh eggs? You did.
We could probably do it quicker with that.
You could absolutely do it quicker, and it would be far more stable. So, as we know, when we make a meringue, we end up, if we leave it, the bubbles start to pop, yeah, and then you end up with what at the bottom?
The soggy bottom.
The soggy bottom.
Yeah.
As this, because it's dehydrated, you're rehydrating it, and then as it oxidizes, the bubbles solidify. So you have far more stable bubbles, which can take a lot more, they're more resilient. So it will stay emulsified for longer. Yeah. So I'm just going to introduce a little bit of water back into here. I've lost.
Can I help?
Oh. Yeah. So it's what's known as a 10%er. So for every milliliter that you would use, I'm using 300 millilitres here, you'd use about 30 grams. Okay. So I put about a tablespoon and a little bit in there. Now you can use hot water, cold water. It doesn't have a reaction rate to acidity or to alkali.
Yeah.
So what I'm going to do to demonstrate that.
So you can add acid and alkalis to this, and
it will
won't
still emulsify.
get in the way.
Yeah.
Right.
So
That's
I'm
brilliant.
I'm going to add a little bit of concentrated mango, which is very high acidic, just to demonstrate that it will still react the same way. Now, during the war, the reason that they powdered egg was
to preserve it because they
preserve-
didn't like the taste of varnished eggs and all the other things that they used to keep under their beds. You know, preserving food because these things weren't readily available.
Yeah. So as you can see, that egg has already started to emulsify with the water. The more I beat the air into it, the more it starts to foam. Yeah? Now, I don't know if anybody's whisked eggs before, but it's a lot harder than this. Yeah? And it takes a long time. Yeah.
Right.
So you can smell that mango. So that you can smell how high the acidic level of that is, and that will stabilise. And you will bake it, and it will just come out like a normal meringue.
Yeah.
You can add hot sugar to it at 118 degrees, and it will make an Italian meringue. It will react exactly the same way, if not better, than a normal egg white would. And the fact of the matter is, in its essence,
Let's put it down there.
it's cheaper. Because the shelf life of that, compared to an egg, is immense. Yeah? I've had this for 2 years, and it's still working.
So this is really, when we talk about acidity, you might hear people talk about low pH, because when things are acid, we refer to it, it's a bit sort of counterintuitive, but we refer to it as a low pH.
Yep.
So when you see a low pH, that means high acidity. And high pH means low acidity. And it's really, I mean, we're going to see in a bit, aren't we, how relevant all of this sort of...
Yeah, definitely.
Add too much acid to something, like jelly, and it doesn't work. And hopefully I can explain why.
Science, much like cooking, is a fine balance.
Yeah.
If you change the ratios of your ingredients when you're baking a cake, your cake won't work. It won't rise. You won't get the reaction that you're looking for. Now that reaction is scientific based.
Yep.
It works the same way across everything else. Yeah.
So we've looked at albumin, but for me, when I was young, I was taught if we wanted to thicken something, we'd use corn flour, which, you know, had its advantages because it was cheap and readily available, but it also had its disadvantages, and you're left with sort of opaque sort of sauces, and you knew when something had been thickened with corn flour, and it didn't actually give a lot of taste to stuff either.
No.
And it was a tendency, probably as much in industry as anywhere else, to put too much thickener because that meant less of the cream or the other or the stock or the more expensive ingredients.
And they've tried many others as well. Arrowroots.
Absolutely. So we've got
monosodium glutamate.
Well, I remember a little bit older.
Yeah.
Marco Pierre White and all the sort of, what do they call it? Nouvelle cuisine.
Yeah.
And I had a friend who worked for Marco because he worked in Yorkshire at that time.
Yeah.
The box.
Oh, the box tree. Yeah.
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 And my friend worked in his kitchen, and he used to cook me like meals that he made. It was all peach brandy and arrowroot and funny little birds that I didn't know what they were.
Ortisan or partridge.
Yeah, that sort of thing. But the sauces looked brilliant because they looked translucent. You could see through them. They were like lovely clear sauces, and everything looked more delicate. So.
But how was the texture? Did it have a gluiness to it, or?
I think it probably had a little bit of jelliness to
Yeah,
it. You know, when it cooled down.
Yes, yeah, absolutely.
So on the plate, if you left it, it wouldn't be as attractive.
We'll be talking about the reaction rates when they're warm and how things solidify when they go cold, and that's definitely apparent. Definitely.
So it's how things look. This is being. I mean, all of this is being. This idea of molecular gastronomy is how it looks.
Yeah.
And there's some weird textures as well.
Yes, definitely.
So then we had, what was it, gelatin?
Yep.
So gelatin's not to everybody's taste, particularly if you're a Muslim, you don't want, or Jewish, and you don't want to eat.
We know where gelatin
pork.
comes from. Primarily pig's trosses. Yeah, it's the extraction of pig's trosses.
And this was the sort of reasoning behind what was it called? The Andrea.
Oh, Ferran Andrea. The Nouvelle cuisine.
Yeah.
Avant-garde cooking.
Who set up his El Bulli kitchen in Spain, which is where basically the molecular gastronomy came from.
Yeah. I mean, the avant-garde revolution, as he refers to it, was primarily a college. It wasn't meant to be a restaurant. but the steps he was taking in the creation of different products to stabilize, emulsify, set, gel, and spherify, as we're going to talk about in a minute.
And make vegetarian.
It became a collection of just a new style of cooking. So therefore, he wanted people to experience it. But El Bulli notoriously had 40 chefs for 40 customers, full stop, because he wanted to make sure that not only was the food being provided at the most exceptional rate and standard, that the chefs were learning, because he knew the more chefs he had, the more would go out into the industry and the more would change. So people like Heston and Mark Sargent, Tom Kitchen, a few other people in the Michelin area all went and did a season of El Bulli, and they brought it back into the industry, and then that's where it's become this revolution.
So the main point is we're changing stabilizer. So instead of using the sort of stabilizers we've been talking up to now, we're getting rid of the gelatin. We're not, I'm sure you still use gelatin in lots of ways.
Yes, yeah.
Well, good stock's full of it, isn't it, anyway?
Oh, definitely. And if we're using a pork product, then we'll use gelatin.
But for vegetarians and for people, I mean, we mustn't forget vegetarians here, because being able to make nice textures for vegetarian food is an important thing. Important in future. India's mainly vegetarian, aren't they?
Yeah.
Massive, huge population.
Yeah, and there's a massive region that's vegetarian, and there's pescatarians as well.
Yeah.
That would still need the setting agents.
Yeah, still wouldn't want things like that. Yeah. So they drew on something that as scientists we've been aware of for years, but for centuries really, and that is agar. So agar as a thickener, or stabilizer should I say, using the correct terms, is what molecular gastronomy is all about. And being able to use this agar to produce new food with a different look, food with different textures.
Just pass that one.
So basically, I've given a bit of a clue, but where do you think we get agar from? It's seaweed, yes. So we get it from a chemical called, the chemical that we refine from the seaweed is called sodium alginate. Alginate. Alginate, sodium alginate. And when we talked about doing this, we basically set the bench in terms of science, because I find a lot of, when I read articles about things like this, the journalists hook onto words that sort of evoke a mastery of science, but actually make the whole thing very difficult to understand. So I've decided, or Paul and I have decided, that we would try and keep this as level 2, and nothing more, because that's where the science sits, basically, that you need to use for all of it. You can explain everything, at level 2. When we do some stuff with Jim, when we talk about proteins and the way they change, it may be that we need to talk a little bit about level 3, a bit more understanding about the sort of intermolecular forces that go on with tertiary, the outsides of proteins in the tertiary structure, stuff like that. But that's when we need to talk about that sort of thing. So at the moment, this is what we're focused on. Now this basically is a complex sugar, sodium alginate. It's another way of describing complex sugar, and I'm no biologist, so I won't go any further on it, is polysaccharide. Yeah? So this seaweed contains this polysaccharide, which I'm sure you've seen on the back of ingredients, and this polysaccharide basically looks absolutely horrible. A very worrying sight. We won't be dwelling on this, but basically these long strands allow substance. We'll get this just to illustrate. The substances that you make with this stuff to be sort of springy and jelly-like. So you would expect it to have plenty of give. Yeah. So that's what agar. We call it agar gel upstairs in the science department, but this is the sort of thing that the agar, the structure of agar, is going to bring to whatever we're making. And Paul's going to show you some use of. I'll keep this with me actually. Yep. Quite like holding this.
Okay.
It's almost like it's alive. This agar can be used in various ways. So we're talking about the early stages of using agar here. There's more to go. There's more chemistry involved, if you like. Mm-hmm. But initially, we're talking about more the sort of ways we can change the appearance of it.
Definitely, and the ratio introduction of it as well, because as chefs, our language is ratio. So how much of one product do we put into another product to change the molecular structure of that product, whether it be by time, temperature, or the introduction of another source. Okay, so I'm going to go from the extreme, well, not the extreme, the highest introduction of agar to a product and where it will take you, and then we're going to slowly come back, and then we're going to talk about a little bit of spherification. But first, I'm going to show you what agar can do as opposed to gelatin. So I've made some set agar. Okay, so agar, the way it works is you add 3 grams to 300 millilitres of neutral liquid. Okay, if you're going higher on the acidic level, you will need to add a little bit less. And if you're going a little bit more, and if you're going lower on the acidic level, you add a little bit less, but only by about 20 millilitres. Okay, so we've got 2 different types here. We've got a high acidic product on the top, which isn't as set as the lower on the bottom. So this is an apricot, this is a raspberry. Okay, so what I was going to do is I'm going to demonstrate that you can set agar, and then you can actually introduce a liquid that's in flame to it, and it won't melt. Whereas jelly, as you know, if you start to get it out, if you touch it, if you put it in your mouth, it just starts to dilute and disappear. Okay, it's not as stable as agar itself. So I'm going to use a little bit of Cointreau. Okay.
Oh, going to heat the Cointreau. Do you need to set fire to it? Or
I will be setting fire to it, but I'm just going to warm it up a little bit first, just to give myself a head start. Okay, and then once that comes up to temperature, I'll light these, and then I'll drop the lights down so you'll be able to see the flames on top. This is one technique that came around, and I would say that this is probably one of the first techniques that came around in terms of avant-garde cooking, where they learned that this setting agent didn't just allow for vegetarians to have it and for it to go for set jellies to go to a wider market. It also allowed for such theatre as this, and then theatre and food was born. Now food is an experience. It's not a case of, oh, the food tastes fantastic. Not really worried about the table or the ambience. The food was great, and that was our evening. Very Delia Smith. Now, everything is an interaction in the restaurant. So the food should be doing things that it's never done before. Yeah, it should be bubbling. It should be foaming. It should be bouncing around the table. You know, these are all things that the introduction of these products have allowed us to achieve.
So basically, you can vary the texture with acidity, alkalinity,
yep,
and with the amount of agar that you're adding.
Yes.
To your substance, to your mixture.
Yeah,
right.
Definitely. Right, so we should have a little flame here now. If I set the fire alarm off, please don't worry.
Tell me when you want me to switch the lights down.
Turn the lights down.
Oh, beg your pardon.
This is the problem with having a smart building. Okay, so as you can see, the flame is on top, yeah? And the top gel will start to melt before the bottom gel, yeah? So the top gel that has a higher acidic level is less stable, yeah? The lower acidity level at the bottom.
You can see it dripping off.
Yeah, and it's just starting to go now.
Just turn it slightly.
So
Oh yes, it's all running. Yeah.
And if anybody would like to come and taste it, they're more than welcome. Yeah.
Is it still on fire?
There's still a tiny bit of flame there. Okay. So that's one example of what we can do with agar. And now that is quite basic. That's basically swapping your gelatin setting agent for agar and ensuring that you've got the all right texture. Agar does have a horrible texture if you add too much, and it can almost taste a little bit claggy. Okay.
Just done that as a almost set jelly.
Yep. Yeah, as you would. As I say, the apricot is more towards the neutral level. So that was 300 millilitres of apricot coulis to 3 grams of agar. Bring it up to 63 degrees because you do have to activate agar. Yeah, it doesn't work where you can just add it and then it will start to work. It needs heat, it needs energy for it to start to do what it needs to do.
May I try one?
Yes, absolutely.
Thank you.
You can either try the ones in the Cointreau or there's some here in the plate as well. Okay, have a taste.
I'm going to try that.
And you can definitely feel the difference in texture between the one on the top. Is it raspberry?
Yeah.
You can feel the raspberry texture.
Yeah. And the apricot should almost be like an apricot, like you get off the flesh of an apricot, you know?
Yeah, it really is very soft the top, isn't it?
Yep. Okay. Are we doing the setting? Or?
So should we do some soft?
Yeah. Excellent. Okay. Now this is my fun part. There's a bowl of ice in there.
I'll
Could you
move
just pass it out.
back here. A bowl of ice. I'll get it.
We just need to add some water to it as well.
Ice and water.
Yeah.
I'll do that. Is it filled to the top with water?
Yes, please. Yeah, it's just to submerge. So I'm going to take it. This is again the raspberry coulis. All this has in it is agar. Okay. So I'm going to add some of that to the pan. Just a touch. Just to activate the agar. All right.
Is that okay?
That's perfect. Yeah. In fact, I'm just going to put a little bit of this water in here because the dilution will allow us to see it a little bit clearer. And then I'll add a touch more agar. So as I said, it activates about 63 degrees. Some people use it as to do a fluid gel on a plate, so they keep it as quite a loose product. But again, if you get it wrong, it can have a horrible texture. So if anybody's ever used monosodium glutamate or arrowroot before, if you get the ratios wrong, what you end up with like a wallpaper paste. And it's just not enjoyable. I mean, there are cultures, you know, the Japanese absolutely love anything that's slimy. They love that texture in their mouth. But in the UK and well, in America as well, it's just not our cup of tea.
No.
You know, we like things that we can control.
Like a lot of fish can be like that, can't it?
Oh, definitely, yeah.
That's all about texture. I think people that are squeamish about fish,
Yeah.
it's about texture.
Well, there are now. There's a restaurant in I think it's in Hong Kong where they have a whole menu that it looks like salmon. It has the texture of salmon, but it's agar and it's completely vegetarian.
Yeah.
The whole restaurant, and they've managed to make sausages and burgers and the right type of texture, both setting agar, pushing it through a mince. And they make
So
it
it's
look
really
like,
transforming.
oh, definitely.
Because you know, stuffed peppers, you know, with a little bit of red pepper in it. That's not red pepper. That's pepper puree that's been set with agar.
Yep.
So that's really easier to do in industry, you know, rather than humping around loads of peppers.
We are constantly, as chefs, having to play catch up because if we don't stay with the latest trend,
Yeah.
then we're just going to get lost. Yeah.
Ooh. Oh, I can't do it, me.
So if I put it into the syringe first, then it might be easier to inject it.
Right.
So I'm just going to suck the fluid up into the syringe. Now I can see that agar has started to activate. Oop, excuse me. If you're in the front row, you were going to get wet. Okay. Moment of truth.
Right, softened, I get you.
Yeah.
And then you're going to, shall I hold it like that?
Yeah, so what we're going to do here is we're just going to fill the tube.
So put it just in front of that camera.
Sorry, we're going to fill the tube with the agar liquid. And then much like a jelly mould, yeah, we're going to cool it down at a rapid rate. And it should solidify like a jelly.
So I hold it in.
Yeah. And then that should take a couple of minutes, I think.
Because this stuff doesn't melt until it's, what, 85 degrees or something?
Yeah, at least.
So you can make these gels and put them into hot things.
Yes, definitely,
Yep.
definitely.
Because you were
I
talking
mean,
about...
people, they will do like a ballantine of chicken,
Yeah.
and they can put a basil gel down the middle. Because as we know, the centre of a chicken breast should be about 73 degrees, yeah, for it to be cooked. But that jelly won't melt because with the residual heat around it hasn't gone above 85 degrees. So the strangest thing on the planet to cut into a chicken breast and find a jelly in the middle, yeah, that's solid.
Or some chicken soup, or
Yes.
consomme, and have a chicken noodle.
Yeah, I mean, this is a lovely bit of theatre that I personally like to do. There's a small cup of chicken consomme, which is a clear, rich, beautiful soup, and they make a chicken noodle that will sit in the cup but hang over the edge. So as the customer gets it, they can suck that noodle up, but all they're getting is that the dilution in their mouth is chicken. You know, they're expecting like pasta or starch or something like preconceived idea, but you're changing that mindset. So they get this chicken and they're like, whoa, that's an experience I've never had. This sense shouldn't be working with that sense. And before you know it, you've created something new. Yeah? So I'm just going to let that cool down a little bit.
Right, so in the meantime, I'm going to, if somebody could come and help me, just cut a bit of gel, agar gel. So we'll have a look at, I can't find it, whereabouts is it?
It's here.
Oh, there. Right, to have a look, can I have a volunteer? It's not going to hurt you, this.
Yeah, there's no high risk involved, don't worry.
So, what I'd like, this is set, wear gloves. Oh, you'll do it, brilliant, thank you very much.
I'll learn something.
So, what I want you to do is cut almost cubes if you can. Try and cut them, it doesn't matter about waste, try and cut them as straight-sided as possible so it looks better. And I'm going to set up some nice, strong hydrochloric acid. Can I move
Which
your food for a
I
minute?
don't cook with.
Oh, how many are you wanting?
A couple would be lovely, but one is sufficient. So this is hydrochloric acid, a little bit stronger than the stuff in your stomach. And really what I'm illustrating here is how liquids or chemicals get absorbed by things like this agar gel. This is the same sort of stuff as Paul's been using. That looks wonderful, thank you. I will take those, thank you, and I'll plop them.
I love the colour.
Oh, I should explain, thank you. This is an indicator. This is basically agar gel that's been made with some alkali. So the high pH stuff, the opposite of acid if you like, and we put indicator with it so it goes pink. But if it goes into acid, it starts to change to a clear, a beautiful, well, beautiful clear is clear, but the pink's beautiful anyway. So when I bob these in here, I did move the food. When I bob these in here, what you're going to see, and it's really to illustrate the penetration of the agar by other chemicals, which is exactly what Paul's going to talk about in a minute, which is this spherification. So it'll happen over a couple of minutes, but you'll be able, because we've got an indicator there, you'll be able to see how the acid penetrates the agar jelly, because you'll see a clear layer forming. You can already see that, can't you, from the front? I'm going to wash my hands because they're stinging. because I've got some alkali on them.
No worries.
So it won't be a second.
Okay, so while we're just waiting for Simon to do that, this noodle should, in theory, be ready. Okay? But the best laid plans of mice and men. Okay, we may have a liquid, we may not. If it doesn't work, I can point you to a great YouTube video where it does. Okay, so I can see that this has got a bit more rigid. So I can see that there is some solid structure in there. All right, it's not pouring out. So fingers crossed. You just get an empty syringe. Now again, this noodle will only work if you get your acid levels right. Okay. Now we should get, if we build up enough pressure.
Oh, yeah.
There we go.
Oh, that's wonderful.
Okay.
Can you all see that? So we've got fruit spaghetti.
Yeah. So you've got raspberry spaghetti. Okay. Good for vegetarians. Great for anyone that likes a strange fruit salad. Okay. Now, would anyone like to volunteer? Yep. Okay. So if you come to the edge of the plate, and just like you would with spaghetti, I'll get this end. We'll do Lady and the Tramp. Okay. No. Go for it, Paul. Okay. And no. Whoa, you've lost control. There you go.
Hey, it's quite
have that one.
strong,
Have this
isn't
one.
it?
Yeah. I mean, it has a structure to it.
Does it taste nice?
And then it should just go to a raspberry in your mouth.
Yeah.
You're not that keen on raspberry then?
It's sour.
Yeah, very sour. Okay. So,
Right, so you've got hard agar, soft agar, and basically this is all about how much of the agar powder you put in, how much of this sodium alginate, which, as I said before, forms this springy substance. But this isn't where, doesn't look good, does it? Hydrochloric acid on the work surface. So far, we're just changing the appearance and texture of the agar, if you like, by altering the amount of powder that we're putting in it. So that's sort of probably the sort of starting point, isn't it, of Ferran Andrea?
yep, definitely.
But then what he wanted to do is he thought, how can I go further? How can I make new, drama? How can I make new structures? And he started looking at these ideas of spherification. So basically making that's my cubes at Holiday Snaps. Can you see, everybody, that these are working in a similar way? You can see the acid penetrating the agar. And the indicator is changing colour. Now, what we're looking at now with spherification is not just changing the concentration of the alginate, the sodium alginate molecules that I showed you, which were like strands and they were springy, if you remember. But we're going to change the structure a little bit. Now, this could be quite complicated biochemistry, but I think I want to illustrate it in a fairly straightforward way. What Ferran Andrea found was that if he introduced calcium ions, as in the nutrients, you see it in lots of food, lots of vitamins, that sort of thing, the nutrient calcium, or basically more specifically calcium ions, which are represented here as Ca2+, they're a group 2 metal. If you introduce those ions into sodium alginate, something happens. Now, calcium likes to make 2 bonds. So, could I have some volunteers, please? Right. Would you like to hold one end?
Yeah.
And just stand a little bit further back, but so your side on, is that okay? And would you like to hold that end? That's fine. So what we've got here, let's say, is a strand of sodium alginate. So you can pull it, it's quite springy, isn't it? It's nice and springy. So if you stand up, pretend you're a calcium, okay? So you stand up, And you as well, please, at this end. So, and I want you, because you make 2 bonds, you've got 2 hands, to grip it like that. And that's essentially what the calcium does. So you grip it, and then you grip it, maybe a little bit further along, and then if you grip it, go on, have a little go. And you grip it, so you're gripping on nice and tight because it's bonding now. And now if you try and pull, you're not getting the same springiness, yeah? This essentially is rigid, really, you know, between the hands. So calcium ions, if you expose the alginate to the calcium ions, you get this effect. Instead of it being springy and jelly-like, like this lovely fruity spaghetti, I won't eat it because I know it's been near this, but I want to.
Yeah.
Maybe I'll wait till nobody's looking.
There's plenty of other stuff now.
But so you lose the springiness, and you can start messing around with the texture of the alginate by exposing it to calcium ions. So this is the principle. Thank you very much. This is the principle that Ferran Andrea used when he started a process called spherification. Now, would you like to explain? And I'll interject with various points of science.
Yep, definitely. We'll talk about, first of all, we'll talk about standard spherification, which is the application of agar into your product reacting with calcium in your bath. So your bath is just a neutral pH. So, and then you introduce your calcium, which will react with your agar.
Brilliant.
Now, because we've got a high acidity rate in this agar, we've also added, xanthan gum.
Oh no, we've added some sodium citrate.
Sodium citrate, sorry.
Yeah, because so I talk about that. Mention
Yeah,
that?
yeah, just.
Well, basically, what's happening? I was telling you that the calcium sort of bonded, if you like, to the sodium alginate and made it more rigid. And they form these 2+ ions, right? So if you've got a lot of acidity or high level of acidity, you have a lot of hydrogen ions. That's what defines acidity. You don't need to know too much about this, but the hydrogen ions, the H+ ions, interfere with the calcium bonding on. And instead of calcium bonding on to the sodium alginate, you get all these H+ ions bonding in there. They get in there first. So if the acidity is too high, there's too many hydrogen ions about, and they will just interfere totally.
And the reaction doesn't take place.
And they don't form 2 bonds, they just form 1 bond, so they don't have any effect. You know, I could make you all stand up and hold on with one hand, and the effect would be nowhere near the same, because it would still be springy, because there'd be no 2 points being gripped.
So in effect, before you introduce something to the bath, it solidifies at a very low end, and then as you try to take it out of the bath, the molten middle dilutes into your bath, and you don't end up with that structure.
So you've added sodium citrate, which basically mops up all the hydrogen ions. It forms what we call a buffer solution. It mops up all the hydrogen ions and allows you to work with products that have a higher acidity or a lower pH.
Yep. So I don't know if anybody can see in this bath, there's a small diluted product which is floating in there. Okay, so that is this that I added about half an hour ago.
So your bath is full of calcium ions?
Yeah, absolutely.
There's loads of calcium ions.
Loads of calcium ions in there. So that reaction, as soon as this hits that, starts to take place. Those calcium ions start to jump onto the edge.
Yeah.
They form a structure around the edge, like a balloon, but it's a structure of itself. So one of the things that Ferran Andrea sold this product as with spherification is it's the product speaking for itself. So it was the first thing he did was a pea puree, which he put into the bath. He'd give it to the customers. They'd have it as a little balloon structure that would pop in their mouth, and the only thing their mouth was full of was pea puree. Yeah? Or in this case, I think that's like a mango. Yeah? But this time we're going to be using the raspberry.
So you can see how it's a calcic, isn't it?
Yeah.
Yeah. How that is. This is how it would sort of be absorbed into the pea puree and be turning it from being soft wobbly pea puree to being firm and hard and forming these little caviar balls.
And it's not just caviar balls. You can make the spaghetti much like we have here by simply running into the bath over and over again. But you have to allow this reaction time to take place. It's a fine balance of leaving it in there long enough that you've got that film on the edge of itself, but that reaction's still taking place. That grey structure that was in there earlier is because the reaction has been taking place and taking place and taking place and taking place until you end up with a rubber ball, much like you see here. Okay?
So that will carry on until all the pink disappears. So essentially, if that was your agar fruit,
Yep.
the calcic would work its way all the way in
Yep.
until everything was just solid.
And there was two problems that Fer and Andrea encountered. One, these things had to be made to order. So they had to make it and send it to the customer before this reaction continued to the point that there is no liquid center. Yeah? So he didn't want to serve his customers these, yeah, because he's selling them as a liquid center, but they bounce, yeah, like a rubber ball. So he came up with a different scenario. So the second problem was if he was using something with calcium in it. So if he's trying to make milk spheres or milk caviar, it already has calcium in there. So if he introduces it to a calcium bath,
Sorry, well, if he introduces the
the
agar to
into-
it,
yeah.
it'll just set solid straight away,
Yeah.
like one of them funny.
so the
milk bottle
reaction
things that you
takes
get
place
sweet.
instantly. Yeah, he's probably used it in another product, in another variation. But for this spherification of anything with calcium, he had to invent what we call internal spherification.
Or reverse as well, isn't it?
External spherification. So the reverse. So if you imagine
Sorry,
this reaction, no,
I'll
it's
move
fine.
that out. Sure.
Yep. So this reaction is going from the outside in. Yeah. So that agar is being, the calcium is almost eating away into the agar, and it's setting it solid. By simply swapping them around, so I've put the agar into the bath, the calcium into the puree, the reaction is going external. It's going out. So as long as that agar, as long as there isn't more agar sat around it, the reaction won't go any further than the calcium ratio can put out. Yeah.
So basically, when he was saying that it's the product speaks for itself with the normal spherification,
Yeah.
because that's just basically a ball of the product.
Yeah.
What you've got with the reverse spherification is the product, which is going to remain a liquid unless it comes in contact with the agar, because at that point the agar will turn into a solid. So you get a film of agar around a liquid centre of whatever it is that you're making, which is brilliant if you need something that's got a lot of calcium ions in it.
Definitely.
Yeah.
But the dilemma as a chef is this can be a little bit wallpaper pasty.
Yeah.
So you have to introduce so much agar to the bath
Yeah.
that you do get this gelatinous film almost.
And you probably need an awful lot of calcium ions in the product that you're trying to spherify
Yeah.
in order for it to do it properly.
Yeah,
anyway.
definitely.
But we found that earlier on today we were adding sodium citrate here. And,
Yeah,
you know,
yeah.
this a bit too acidic. But add a bit of that. You know, it's just like it's chemistry.
Yeah, definitely. I mean, you know, it's something. It is a whole world that has opened up science in cooking. People like Heston Blumenthal would not be in place without this. Not because he's got access to these, because Heston Blumenthal is a scientist that's learnt to cook. He's not a chef that's learnt the science. So he's come from the other side to us, and he's brought these ideas, these techniques, these infusions and reactions to us. And Fer and Andrea, much the same.
Yeah. So I think that we should look at lots of different areas of cookery, and
Yeah,
I mean, there's
definitely.
lots more in terms of this, but there's no point in doing too much in one session, you know. But I think we should do some more
Yeah,
where we look at the science and how, because I mean, this is just science.
Yeah, and this is just the tip of the iceberg.
Yeah, yeah, absolutely.
Does anybody have any questions?
Is this what, you know those Japanese teas you can get?
Bubble teas. Yep,
Yep.
yep, definitely.
How much are they?
They're for £2.10, I think, for a standard tea.
So they're doing it quite cheaply then.
Yes, yeah.
Because I think that all this stuff lends itself to an industrial level. You know, buying these, because I mean, can you imagine how quickly a factory could push out loads of these little balls?
They must be doing the externals verification with it though, unless they're using a different stabilizer, because that reaction would continue. If they made it in a factory, by the time it reached the shop,
so you can't.
they would be rubber balls. But they're not, are they? They're bubbles.
Internal verification.
They use internal.
It gets just 1 point and then it just stays.
Yeah.
So you've just got a little bit of like a syrup. on
So the
inside,
reaction's going.
quite a thickish shell which just dissolves.
So it's this one. Yeah.
Very interesting.
But again, that trend probably wouldn't have come around if it wasn't for Ferran and Andrea bridging the gap between those things.
But what about cocktails?
Oh,
I mean,
definitely.
You know,
Yeah.
can you imagine sort of fancy cocktails with all this sort of stuff?
I mean,
in them?
combining the two, actually, the start and the finish, a great cocktail is a caviar like this in a CO2 product like Cava or Prosecco.
Yeah.
And the reaction you get is the CO2 carries the caviar from the bottom of the glass to the top in a rotation. So you get this lovely little theatre
Get a little lava lamp.
going on. Yeah, like a lava lamp within a flute.
So can you make that sort of popping candy? Is there a way of doing that on a small scale without having using 600
Ooh, I don't
psi pressure?
Yeah. No, I don't know. I've never tried to make. I mean, I can make
But
it.
you'd buy it in and flavour it.
The only reaction I can think of is that when we make not brandy snap, honeycomb.
Yeah.
We make caramel. We take it to about 160 degrees, and then we introduce bicarbonate of soda. So the reaction there is the aeration
carbon dioxide
of the
out,
sugar. And that's the only time I can think I personally would look for a reaction like that. And then if you leave too much bicarb in there, you get horrible flavour, but you do also get the fizz. So I think without some high pressurised machine, no.
Think of the future.
Yeah.
That's what you can invent.
But again,
Make a million.
that's why they can charge so much.
So when you do the external
It's verification.
will those little balls keep for a little while?
Yes, they will.
That's
Again, it depends on the product you're using. So if you're doing something like a cucumber, a coulis, something like that, quite a while. But if you're doing something like a balsamic or raspberry,
The acidity would interfere.
24 hours at the most. Yeah.
And also,
But-
it's a growth medium. We use it in biology. You know, when you see a petri dish with those little discs of coloured, that's agar.
yeah.
So presumably, you'd have to be careful with it from a hygiene point of view.
Definitely. I mean, El Bulli, for example, will have cleaned down, thrown away, and started again the next day. But all this did is it gave them enough breathing space that they weren't. I mean, I said that there was a chef for every customer, but it gave them enough breathing space that they could prepare all the caviars for that service, all the spheres for that service, and then concentrate on other things. Because they became very well known for the spheres and the caviars and this sort of thing, because it was their foundation. That every customer that went to El Bulli, 40 a day, that's what they wanted. So even though they were doing all these great other things, this was their selling point.
This is their, yeah. So you can see here, you can see how it's eating its way into the...
So what was that? Is that 10 minutes?
Yeah.
Yeah.
But I think yours probably goes faster.
Oh, yeah.
I think this is very dense. And if you serve that up for somebody's dinner,
Yeah.
apart from tasting of alkali, it wouldn't be a very nice texture.
Okay.
Okay.
Oh, yeah.
The ways that they also do them for Japanese kind of like all prepared, just they give you the powder,
Yeah.
they give you the instructions, and you can do it at your own house and do it yourself.
Yeah.
So you can change the flavour of it.
Yeah. You were saying to me beforehand that the children, it's become a hobby
Yeah.
for children. Much as ours are doing loom bands and things like this,
Yeah.
that they're now creating different spheres and
Boxes.
yeah.
Where you
different flavours,
make
So you're
a burger and chips or
Yeah.
something, but it's all jelly.
it's all
Yeah.
agar.
They've got little sections in a box.
Yeah.
It's all like disposable. and you pour this syrup into this powder, mixes together and let that set, and it comes out of the mould, and that's the cheese. And then.
And it actually tastes like it.
Yeah. Well, I think it's like a sweet, but it's.
Definitely looks like it.
So basically, you're saying we've got Japanese do-it-yourself kits with that you can make sweets, popping candy, various flavours, and then you can make agar food.
Yeah. And
Just and adding the different flavours in.
It's become a hobby.
Where'd you get this sort of thing?
Online.
Yeah.
You can't.
And the stay, because it's in powder form, it'll stay for ages, and you only have to add water to it.
Well, maybe we can see if we can get hold of one and maybe start the next class reflecting on this with doing one of these.
Well, you could do it in a
Not
posh.
not on the world food aisle, but maybe in one of those American sweet shops or.
Oh yeah, I know
Yeah.
what you mean. The overcharge for American sweets.
Yes.
Yeah.
See, there's YouTubers that promote this. And
Yeah.
I think I remember the website, and you can go on and get it for like a £5 or something,
Okay, we'll go have a look.
Right.
and that includes the shipping.
Well, it's an excuse for Simon and I to have a play around, you know.
But you could actually use this idea, couldn't you, to make to do a restaurant meal?
Oh yeah.
You know, where
Yeah.
you sort of this is more interactive.
We talked. I mean, earlier I was talking about the theatre, the interaction, the customers having an experience.
Yeah.
You know, what better experience is there? I mean, we've done science nights in the restaurant where the customers will create their own
Make their own ice cream. and
their own
things.
ice creams and their
Yeah.
own
Interesting, isn't
cream
it?
eggs and things like that. So yeah, you
You
can
can
do
add stabilisers to ice cream to stop it melting on a hot food, can't you?
Yes, you
Like
can.
that, which
and
is-
foams as well.
So
I mean,
adding stabilisers to ice creams, what stabiliser would you use?
agar.
Agar.
Yeah. You can use vodka as well.
I
can't
don't know
you?
why it is. It's just I once did a session at Leeds on
Yeah.
this, and the lady, she made an ice cream, and she used one of those products. I can't tell you for the life of me what it was.
Yeah.
And she said, you know, you can put that into your ice cream. You can get a perfect bowl of ice cream on top of the hot, steaming hot dessert, and it'll go to your customer,
Yeah.
and the ice cream's not melted.
That's
at all.
agar. It's that melting point again. So the ice cream would probably taste a little bit like if anybody's ever had a Milka lolly, the little lollies,
yeah.
When they start to defrost, they taste very
Bitty.
marshmallowy.
Yeah.
Oh,
like,
Yeah, this because they've got a stabilizer in them because they know
Because it's eggy.
it's a small product. By the time you've got it from the store to your house, it's melted. So they're trying to put this stabilizer in it. So even if it does melt to an extent, when you refreeze it, it holds its shape. But in terms of other stabilizers, like foams that people see, you know, that bird spit that you see sometimes on your plates. In recent years, it's now become much larger structures, and they're starting to get this almost aeration of things like carrot foams and things like that. The way they're doing that is either with gelatin or agar, and they're whipping it into
Vacuum.
yes, but they're whipping that into the product. So when the air's introduced and it foams and it hits the oxygen and it solidifies, those bubbles have that structure that you were talking about, Simon. So it's used a lot, and people don't realise how much.
So if you use some of the raspberry Kool-Aid with the
Calcium.
calcium, could you sort of use a spoon of it, a small spoon of it, and add it to your
To the bar?
yeah.
Yeah.
Bigger.
Well, I was saying to Simon earlier, because with having to use so much agar in that bath, it has a much denser structure. When I drip the coulis into this one with the intercalate with the agar, it forms its own sphere from the motion of going down. You know, like a poached egg into water. So from the motion of going down, the structure comes around like this. This bath, I don't have that. It's denser, so I don't have the coulis falling and forming its own shape. So I'm injecting it in, and by the expansion here and me keeping the coulis going into the centre of the sphere, it's forming its shape that way. So you could do it by putting like a melon baller and then turning the melon baller over, but I would probably always do it with a syringe.
And you can get machines, can't you? You fill them up.
Oh yeah.
And they just go blub, blub,
Panels.
and they just drop loads of little balls into the calic.
Yeah, it has like 100. It has 100 droplets on the end, You plug your tube into one end, your syringe into the other, and you squeeze your syringe, and then 100 droplets go into your water. So you're not standing there all day going, I've got 40 customers in, and I need to... But yeah. Right, well thank you very much, and hopefully definitely Simon and I will be doing more videos, and any ideas that you would like to see, any trends that you see out in the industry that you think, how do they do that? Ask us, because I guarantee there's a science base behind it. All right?